Good morning, everybody. Welcome again to the National Society of Black and Hispanic Physics Conference. My name is Edmundo Garcia. I'm the treasurer of NSHP, and I'm also a professor of physics and associate provost at Chicago State University. I'm delighted to be your MC today and present the next of our talks. We're starting with a presentation that I'm sure is going to set the tone for the rest of the day for an inspiring and productive day. To introduce the speaker, we have one of our student leaders, Winston Harris, who is a third-year student, graduate student at the University of Memphis. And he's going to introduce the next speaker, and we'll go from there. Thank you.
Hello, everyone. Our keynote speaker today will be Dr. Paul C.W. Chu, who is currently serving as Professor of Physics at TLL Temple Chair of Science and Founding Director and Chief Scientist of the Texas Center for Superconductivity at the University of Houston, and as Honorary Chancellor of the Taiwan Comprehensive University System. He is the President Emeritus and University Professor Emeritus of Hong Kong University of Science and Technology. He was born in Hunan, China, and received the BS degree from Cheng Kung University in Taiwan. After service with the Nationalist Chinese Air Force, he earned the MS degree from Fordham University in Bronx, New York, and completed the PhD degree at the University of California at San Diego, all 3 degrees being in physics. He has been working on superconductivity, magnetism, and dielectrics. Everybody, Dr. Paul Chu.
Good morning. Thank you very much. It's a great pleasure to be here to have this opportunity to share with you my experience in the study of superconductivity. I call it the Odyssey, from low temperature superconductivity to high temperature superconductivity, and finally to room temperature superconductivity. It's an exciting journey of discovery. According to one of the most famous American author, he said, this discovery is man's noblest delight, because when you can see something that no one has seen it before, when you were in the place where no one were there before, that kind of excitement, nothing can beat it. And I'm very lucky to be in that journey. And because being a physicist, in my view, personal view, is the best job in life, because you're doing your hobby and getting paid at the same time. This is the thing I'm talking about, mostly contributed by my colleagues listed here. I'm not going to go through it. The first groups are my own groups. At the University of Houston, the Texas Center for Superconductivity, my own group right now. And this is the group, this is another group headed by Professor Zifeng Ren, and we collaborate with Rice University and University of Illinois at Chicago campus, and also University of Buffalo, and also in China, as you can. And in addition, we also collaborate with Professor Yang Hongdun's group in Taiwan. Basically, what we do superconductivity itself is an old and yet full of vigorous field of study in science and technology. Basically, we try to search superconductors with higher TC, which has played a crucial role in the search even after 113 years after its discovery. We try to use this material to generate, to store, and to transport, and to use energy at the highest efficiency possible, and to allow devices to function in the quantum regime to overcome the bottleneck to the world of tomorrow we envision today. According to the famous Russian physicist, the late Russian physicist Ginzburg, who say high-temperature superconductivity and controlled fusion are two physics problems of special importance and interest. He mentioned this in 1971, again in the year of 2000 during the turn of the century. What is a superconductor? As a scientist, we usually try to look at the basic ingredients of a superconductor. You can see superconductor is here. I call it LTS. And then 90-degree superconductor. And then we have high-temperature superconductor, HTS. And then we have room-temperature superconductivity. Basically, we know in the orchestra, you have the conductor, right? And then you cut the conductor into half, and that's the almighty semiconductor. And then you ask the conductor put on the Superman suit, that's a superconductor. That's what I have been spending all my life studying it. And then this is a 90-degree superconductor. And room temperature superconductor, now it's the easiest way, stand up just like that. The main contributors making superconductor more practical can be listed here. The first person here is Cameron Onnes, who discovered superconductivity in 1911. And then the second person is Brent Matthias, as you can see here. And, Brent Matthias, and basically before the high temperature superconducting era, he discovered 90% of the superconducting materials based on the intermetallic compounds. And all the superconductivity was a phenomenon.
Yeah, let me change your microphone a little bit. Let me put this microphone a little bit.
Oh, okay. Okay. Now you can hear me, right? Okay. So then the other three gentlemen, the first Bardeen, Cooper, and Schrieffer, they proposed the BCS theory, which essentially up to this moment still works to describe this phenomenon. And that's the famous BCS theory. And then later on, we'll get to the high temperature superconductivity era, and started in 1986 when Alex Miller and George Bednoff proposed lanthanum copper oxide materials. And then following that, together with my former student, Professor M.K. Wu, and then in 1987, we raised the superconducting transition temperature up to 77 degrees, the boiling point of liquid nitrogen, makes all these things more practical. And then in 2015, and Mikhail Arametz from Germany, and he announced the discovery of superconductivity up to 205 and 3 degrees in some of the hydride materials. So that's the major contributors in this effort. So I mentioned giving you the cartoon of superconductivity, but for superconductivity, from physicists' point of view, they have to possess several basic properties. The first is complete disappearance of, of resistance. As you can see here, if you look at the resistance, when you cool it down of a metal, all of a sudden drops to zero. Really literally drops to zero, not approaching zero. And so you have to have a zero resistivity in this case. And second, complete expulsion of externally applied magnetic field. As a result, one can use this phenomenon for electromotive study, and in addition, and many other interesting devices. And in addition, we usually know for quantum phenomenon, we have to go to very low temperature or to very small dimension. And yet superconductivity, you can feel it, you can touch it, and so therefore people call it the macroscopic quantum phenomenon. And this was first proposed by London and then later on by Josephson in 1962. So in order to reach this state, we have to overcome three obstacles. First, the temperature has to be lower than superconducting transition temperature, Tc. And then the second is the critical current density has to be smaller than certain. If it goes beyond that, you destroy superconductivity. And the magnetic field, we call it critical magnetic field. The field has to be smaller than that in order to maintain the superconducting properties. And basically, you can also imagine that the most important thing is for electrons to form pairs, because electrons are fermions, and they cannot really condense to lowest energy state. So you have to form pair. So therefore, in 1956, Leon Cooper proposed electrons can form pairs through whatever attractive interaction presence in the case. For electron, we always know they repel each other. How do you get these attractive interactions? So all you have to do is just by polarizing the lattice, and therefore the first electrons can go in here and polarize it. So locally, you have an excess of positive charge here. When the second electron comes by, he saw this positive charge, so will be attracted toward, move toward it at a higher speed. And for the first electron, he thinks that he already attracted this electron. This is a virtual picture, as you can see here. Because of this, so they form electron pairs. And it's interesting, back in 1970s, when I bumped into Leon Cooper, invited him to come to University of Houston to give a talk. He told me BCS theory, after his electron pairs, everything was done. The rest was quite obvious. It's quite interesting. So you can see basically here the electron coming through, and then because polarized the letters, and then so then they form pairs, continuous going like this, okay? Then once they form pairs, then they essentially get to a state without bumping into the lattice and move freely through the lattice as if there was no resistance. And so, as you can see, that's how the superconducting state for the electrons, they just move without resistance. And you can see one of my former junior colleagues is that just as if you want to pass a gate, if you form pairs in unison, you can go through easily. But if you don't, they get into each other, and then you get resistance. So that's the general concept. So back in 2004, when the city invited Dalai Lama to come here to discuss science and spirituality dialogues, and I was asked to present a talk concerning on superconductivity. I thought about what's in common between Dalai Lama and us. So I said, essentially, superconductivity, the electron moves in a vacuum, in a state with nothing, you know. So therefore, nothingness is our common interest. So Dalai Lama, when you give him a birthday card, and he was delighted to say, wow, nothing, that's just what I want, you know. And that's why we want no resistance, which was discovered, superconductivity was discovered by Cameron Onnes, as I mentioned earlier, back in 1911. And then general principle, as I mentioned earlier, they have to form pairs. the Feynman diagram shows, then the pair of electrons emitted the phonons and then absorbed by another pair, and then they form another electrons. They form pairs like that. You get superconductivity. Okay, at high temperature, the thermal excitation energy grows, and that means for them to form pairs, as I mentioned, you have to have attraction between them. And then when the thermal energy is too big, it breaks it up. So then you stop superconductivity doing that. So what we really like to have is high TC needs greater pair potential. So for all these years, we're working on how can we increase the pairing potential to get the TC higher. But usually, unfortunately, greater pairing potential leads to instabilities and even catastrophic structure collapse of a superconductor, and that's the end of it. So the challenge is to enhance the pairing potential without triggering catastrophic instability, and that's what we've been doing all this time. For example, before 1986, the TC, you plot it as a function of time, it goes up like this. At that time, the highest TC was 23.2 degrees at niobium-3 germanium. And then by extrapolation, in order to get up to 77 degrees, that's the liquid nitrogen temperature, and you will not get it until 2,200, and even with the very impressive improvement in medicine, it's difficult, at least not for me, to live that long, So at that time, experimentally, the TC record was 23.2, and then the theory predicted TC cannot go above 30 degrees Kelvin. So during that period of time, confidence crisis for most, but a few, and we are one of the group who did not believe that. But finally, in 1987, this paper appeared by Alex Miller and George Bednarz from IBM laboratory in Switzerland. They said possible high temperature superconductivity in the barium, lanthanum, and copper oxide system. And based on that, at the beginning, not too many people believed in that report because they were not very well known in the field. And also during that period of time, lots of false reports appeared. So people did not pay too much attention. They were really distressed during that period of time. So when we reproduced their results, and I immediately dropped him a note saying that we reproduced their results. And then apparently they kept this note 10 years later, and then in the 10 years anniversary celebration, George Bednarz gave me this note, a copy of this note, saying basically we reproduced their results, and I'm full of hope. I believe, but the physics and the material details were unknown at the time. So then during that period of time, I also dropped my colleague, Wei-Han Chu. Right now he's with Houston. And I said, we got the highest TC of 40.2 K because George Bednarz and Alex Miller, they claim in the 35 degrees range. Now I'm full of confidence of 77 degrees Kelvin. The reason for me to make that announcement to him, by the way, that was December 1986, And because immediately we raised the temperature up to 40.2 degrees, and then later on 50.5 degrees, even though we had not announced it at that time. So this group of materials shows large pressure effect on TC, and hence TC to this high temperature, and this is unpredicted by the theories beyond the theoretical predictions. So in addition, we also look at some of the mixed phase material. We occasionally observe Meissner effect up to 70 degrees, but it was not stable, cannot be reproduced. So in our back of our mind, we said there's no problem, it must be there, but how can we stabilize it? As you can see, even we get up to 100 degrees in a mixed phase compound. This is the Meissner effect measurements. So therefore, observed at 90 degrees Kelvin, with no doubt, we felt superconductivity up to that temperature must be possible. When time is up, just let me know. I can stop anytime, okay? So then finally, together with my former student, M.K. Wu, and so on, we stabilized it in the YBCO material, and with the TC up to 93 degrees Kelvin, and announced on December 2nd, 1987, Physical Review Letters. And that day was really exciting. I should mention, before this thing with my colleagues, particular students, I said, if the day when we discovered liquid nitrogen temperature superconductor, our paper should be only one sentence saying that. But at the time, because I'll tell you this later on, if you have interest, I'll tell you why. But when this happened, we really did not have the courage to send in a paper of one sentence because PIL would not accept it. So March 2nd, 1987, at the time, during that period of time, was called a super day for physics. First, 90 degrees superconductivity was discovered, and supernova was also announced at that time. And then, particularly in the state of Texas at the time, people were talking about the construction of superconducting super collider. So everything is super. So that's why people call it the super day of physics at that time. At that time, the whole world, particularly in the United States, for example, this on the front page, and this is the newspaper, front page, and physics, not Physics Today, And you can see with the pictures and all that saying that jolt of superconductivity. And then later on, then they held a meeting, the March meeting in New York City, and later on people call it Woodstock of Physics. The reason to call it that way, because you can see lots of people going in when the door was open. People packed to the conference rooms, unbelievable. This experience, it's unique in a sense, Now you can see this people rushing into the room, listening to the report. And I'll tell you the origin of Woodstock of Physics in 1987, and that was because we submitted a paper talking about some of the results. And the paper for the contributor talked, and the results was that it was rejected, as you can see here, by APS, okay? They said because your abstract was 1/2 a line too long, Because at the time they have a square and lay on top of the abstract. Anything goes beyond that led to automatic rejection. And they did that. So then my colleague was very upset. What should we do? I said, well, since we couldn't give a contributor talk, why don't we give a invited talk, They said, how? I said, I would call the physics, APS condensed matter physics chairman, Neil Ashcroft. I told him the results, and he got so excited, he said, why don't you organize a special session on high temperature superconductivity? That's how it all started, So now the speakers, basically at the time, they're involved in oxides 5 of them. And I should mention, this is Alex Miller, this is Tanaka from Japan, this is myself, and Professor Zhao from China, and Bedlock from Bell Labs. So finally, I gave a talk there and released our results. People all got very excited. And then later on, the federal government decided to call a conference in July in the same year immediately. As you can see, the president saw the demonstration by Argonne National Labs director himself here, and that was the first time people can really do demonstration like that. Prior to that time, to do the demonstration, you have to liquid helium to do it. It's very difficult. So then with that discovery, we immediately discovered a series of compounds which all have TC higher than liquid nitrogen temperature. And so finally, President Reagan decided to give me the National Medal of Science, essentially to represent the whole field, working in high temperature superconductivity. Then later on, we continued to work on this class of material and refine its structure and also physics. And as you can see, it turns out they're all layer compounds, and all these layers can be grouped into 2 blocks. One is, I call it, charge carrier block, and the other is active blocks, which consists of copper oxygen layers. And these are the active layers. And so later on, many other compounds also with this structure were found superconducting. Particularly, this is the mercury-based compound, as you can see here. And then when we apply pressure to this compound, and the TC actually goes up to 164 degrees Kelvin at about 30 gigapascal, as you can see here, about here. And this means we can already use the air conditioning technology to achieve this cooling. And so that really got lots of excitement for the field. So this was 10 years later, and people still celebrate the discovery of this class of material. So then finally, in the year of 2000, when the White House decided to construct the time capsules to include all the major discoveries by Americans in the previous 100 years. So they also include our discovery in the time capsule. And so finally, they asked me to represent the group of people to celebrate the closing of this time capsules. And as it was held in the archive in Washington, D.C., National Archive. And Hillary was the person in charge of this White House Millennium Time Capsules construction. It was really exciting because right next to our compound was the semiconductor discovery by Bardeen, Shockley, and Breton, So it's really quite unusual, So basically, the event was called to honor the past and imagine the future. So lots of progress were made. I'm not going to bore you with the details of all this, but I can say at the time, one of the major questions is, can there be a room temperature superconductor? And then, of course, people interested in superconductivity. Certainly, for physicists, they are interested in the mechanism of superconductivity, why superconductivity happens at such a high temperature. But for ordinary people, they would like to, what good can it do for my life? So there are lots of interesting stories. So therefore, lots of prototype devices have been constructed and tested successfully with superior performance to their non-superconducting counterparts. And I think right now, one of the important things out there is for the control fusion. Control fusion would not be possible without the success development of high temperature superconductivity. Now, just show you some of the, here you can see the MRI machine, usually, but turns out the MRI machine, you can just have a styrofoam cup filled with nitrogen and put a little device made of high temperature superconductor. It can image the brain of a mouse, as you can see here. You can also image the heart function in this case, This is one of our former students, as you can see here. But the interesting thing is this, I actually use myself as a guinea pig and take my magnetocardiogram, that's my heart's picture. As you can see here, this is my heart's picture, magnetic cardiogram, MCG. It looks like this. One of my colleagues, actually, he had a problem with his heart. But under medication, according to the EKG, just like mine here, no problem, the same. But when you look at MCG, they are so different. So therefore, it contains more information than EKG or ECG, whatever you call it. Okay. Of course, you can use it for many other things, including transportation. And for example, this was I was shown what the Chinese was building their transformer and also a transmission line in southwest China, And then here, the U.S. also trying to electrify their ships. In order to be able to do that, you have to build a superconducting motor. And you can see superconducting motor, and size can be much smaller. The conventional one is here. This is superconducting one, like this, compared with person. And it was being built and tested, in here. And in addition to that, the United States at that time also was thinking about building the grid, using the high temperature superconducting grid to transport electricity. Essentially, you build something like this, a big grid, and then connect it by little things here, essentially superconducting grid, and will save you energy and improve its safety and all that. So going like that, then you can see. So then finally, we get to room temperature superconductivity. How much time do I have now? 30 minutes, so I can go slowly and tell you some of the interesting thing here, okay? Okay, room temperature superconductivity. Of course, if we have a room temperature superconductor at this moment, I think we'll have a revolution develop. Nothing can compete, including the past industrial revolution, can do that. One of the basic element people are paying attention to at this moment is hydrogen. Because hydrogen is the lightest element in the periodic table. It was first discovered by Boyle. I think people study chemistry, knows Boyle's law, It was discovered by him in 1671. And then Cavendish in 1776 in England separated as a separate thing, over there. Then at the time, Bernal, he has a conjecture. He said, everything, if you squeeze it hard enough, it will become metal. He said, can we make hydrogen metal? So he proposed, all we have to do is apply pressure. At the time, people also developed an electron model, single free electron models. They said it's possible. So therefore, Eugene Wigner and Huntington, both from Harvard, from the United States, proposed if you apply 25 GPa, then you can make it into metallic form. At the time, people cannot get to that high pressure, So later on, people use Bridgman, it get up to 50 GPa, and then later on using diamond emerald cell, and then get it up to almost tera GPa, but they had not been able to get it metallic form. So in spite of the fact, a few years ago, a group of people from Harvard mentioned they got the metallic hydrogen up to the 500 GPa, but they only claim they only saw it once, and then it disappears. So therefore, it's still a question. Then the second thing happened, that is, what about superconducting hydrides? Because pure hydrogen, you squeeze it, even to that high pressure, it's not even metallic, let alone superconducting. So therefore, people think about different methods, doing it. And actually, the person first proposed to get metallic hydrogen and also metallic hydride superconducting was Neil Ashcroft at Cornell, like in 1968, when after BCS theory was proposed in 1957. And he said, well, you look at that, you look at the formula, you can get it. It should be superconducting. Of course, it did not happen. And then he modified it, and then in 1983 and 2004 and 2004. And then finally, this, it should be superconducting by using chemical pressure. And that's exactly what we did in the cuprate situation. But again, there was no metallic hydrogen or compound he proposed become superconducting. So finally, in the year of 2015, and Arametz from Max Planck Institute in Germany announced he got superconductivity in hydrogen-3 sulfur compound, and with a transition temperature at 203 degrees Kelvin, under a pressure of 155 GPa, and he announced that. And then immediately after that, in 2019, and Hamley and co-workers in geophysical lab, and then later on they were in University of Illinois at Chicago campus. They announced they found a compound lanthanum hydrogen-10 and superconducting with a transition temperature at 260 K. When the pressure goes up to 180, or between 180 and 2000 GPa. And so this goes on, and lots of claims of superconductivity above room temperature follow all these things, So now if I plot the superconducting temperature record as a function of time, and you can see this plot, originally when it was discovered, it was 4.2 degrees, and then later on continued to increase. And then later on, when the copper, when we came into the field and we raised the transition temperature from 4.2 degrees all the way up to 164 degrees Kelvin, here. I should mention all these highlights with the yellow colors, they were done at the University of Houston, as you can see here. But then recently, when people are looking at the hydride, and then the TC goes even higher, at least they claim to be higher, even up to room temperature, as you can see shown here. And even in one case without pressure, it can go up to 300 degrees Kelvin. And that's really a room temperature superconductor, if it is true, okay? So it goes like that, as I already mentioned to it, and I'm not going to go through these details. But for this hydrides, the most recent announcement involved are those with highlight here, as you can see. It's in the copper sulfur hydride compound, it's 287 degrees Kelvin, and then at 267 GPa, and then there's a lutetium nitrogen hydride, and goes up to 294 degrees Kelvin at 1 GPa. This is really, if it is true, and this is really a very important discovery. And then even in last year, a group of people from South Korea announced they found 400 degrees Kelvin superconductivity. This is really unusual. But the point is, I should mention, right now, there are a lot of doubts raised about these three claims at this moment. So when the hydrogen sulfur first discovered, this Aramets, Mikhail Aramets, because he only measured the resistivity. As you know, with such a small sample under such a high pressure, it's very difficult to do the experiment. So if you can do Meissner effect, then there's no doubt if you can see it, then that's a proof of superconductivity. So I asked Aramets to come to our lab, so we work with them, and then with my junior colleague, Deng, and look at here. We look at 5 of the sample. Unfortunately, we did not see anything. But I did tell him until we saw positive results, I would not make any announcement. So therefore, that's the situation. We cannot. And then this was the person by Diaz I mentioned. They claimed they found 300 degrees Kelvin superconductivity with only 10. That's 0.1 gigapascals. 10 kilobars. So that's, in fact, when they announced these results, they immediately set up a company. They got tens of millions of dollars from venture capital, including Bill Gates and those people, all that. I don't know what they do when this is not true, cannot be reproduced and all that at this moment. And you can see under pressure, they can change color from the sample from black all the way to red and all that. And so, of course, we also follow these things. And then, this is the person, Renga Diaz, okay? So we also follow this. We reproduce the colors change of the sample under pressure and all that, but we could not find any superconductivity happening in this material. So finally, people call it the superconductivity scandal in this case. Now, in spite of that, if all those high-temperature superconductors, I should mention that with all the records, they happen only under pressure. Actually, some of them can be used already, including mercury compounds. If it's really 164 degrees Kelvin at 31 gigapascal, if we can make it 164 degrees Kelvin without pressure, that's already a big breakthrough. So that's what we're doing. And we, at this moment, can we really remove the pressure and maintain the pressure-induced superconducting phase? If that's the case, that would be a big breakthrough, So the idea is this, you see, when you apply pressure, and then at the beginning, it's not even superconducting, as you can see here, in the diamond cell, because diamond cell here, So you put the sample here, you apply pressure, squeeze it, and then finally it goes through a transition, get into a superconducting state, and then you remove the pressure, you try to retain the superconducting state, and that's what we call the pressure quench for high temperature superconductivity and room temperature superconductivity. And that's what we are now striving for, working very hard on. So now we already have some preliminary success. For example, in one of the compounds we did, originally it was not even superconducting, and here. And this is a scale, you really look at 0, it's not even superconducting. But when you apply pressure, it can become superconducting. And then when you remove the pressure, it also remove the pressure, you can maintain the superconducting state and without pressure as indicated here. Depending on the quenching temperature, one is 4.2 and the other is 77 K. You remove the pressure, it's still superconducting. So that's why we are working on getting very excited on that. Now, so basically, if in the mercury compound, when we apply 31 gigapascal, we can get it up to 164. If we can remove the pressure and retain the superconducting phase, then essentially we got it made. And there are several compounds we tried, appearing we can retain the superconducting phase, but not the really high one. And that's why we're doing the hydride at this moment. But with all these things going on for superconducting material, one of the important material, important application is for fusion. Because fusion, in order for it to happen at this moment, people are talking about magnetic confinement. And there's tokamak machine and Lerato machine over there, two types. And in order to confine the plasma, you have to use magnetic field, because the plasma, you don't want it to get in contact with the walls and so on. Only magnetic field can do it, and only high temperature superconducting material can do it, because it has high temperature transition, and in addition, it has strong critical field. And so now people are working on it. At this moment, at MIT, they claim they had some preliminary success in this design and working on that. So with all that, I think I should start. I should end concerning the technical work, because I always feel there is a never-changing rule that in this world, and that is this world is forever changing at an accelerated rate. Whatever can be done today, I can do today, this is also an unchanging rule. Whatever I can do today can be done by you, and also tomorrow, and can be also even better, except age, that thing you can never beat me, okay? And you don't want to beat me anyway, but don't worry, you cannot beat me in terms of age, okay? So in the Chinese poet, they say youth is the most precious commodity in life, But even though I'm getting old, they said a crazily exciting thing happens in life, even when you're old, can make you become young again. And that's why together my junior colleagues were still working on that. We hope that will happen. Right now, it appears to me for us and our generations to come to have a good life, we really want to develop a sustainable world for all of us and for them, And so turns out, as Ginsberg mentioned, two of the most significant and interesting problems. One is control fusion, and then the other is high temperature superconductivity. And we are involved in that, and that's a very exciting area. As I mentioned at the beginning, this journey has been very rewarding. I think I will never change it for anything else, because while I'm doing my hobby and getting paid. And thank you, and I hope you will have that luck too. Thank you very much.
Okay, we have time for questions. I'm sorry, can you put the lights on? I cannot see. Yes, can you get to the microphone? You can get it.
Thank you very much for such a nice talk and very inspiring talk. And thank you also for mentioning fusion. I'm a fusion scientist, so I love the fact that you mentioned fusion. So, but besides all the aspects of applications you can find, medicine, transportation, transmission lines, etc., applying superconducting tapes to fusion will be a true game changer, okay? A really amazing thing. However, fusion has that complication that if you have DD fusion or DT fusion, we have a byproduct called a neutron.
Right.
If you deal with 2.5 MeV neutrons or 14.1,
Yeah.
what would be the state of the superconducting tape upon that neutron flux?
I think this is a very good question. In fact, I raised that question with the head of the fusion office, in Washington, D.C., and he also recognized this point. In fact, now he's forming a task, try to look into this effect on superconducting, high-temperature superconductors' properties, because I do know you are quite right. This neutron actually degrades the high-temperature superconductor, especially in the YBCO material, because this is one of the things they have to overcome. Yes, you are right.
Thank you very much, sir.
In fact, right now they are planning to form a study group in Tucson together with my colleagues, because some of them are making tapes, high-temperature superconducting tapes for power transmission, and some of them look in the structure and see whether we can prevent it or not. But that's a very important issue to overcome.
Hi. So my question is, what experimental technique yielded the highest critical temperature in your material, and why did that technique work so well with that material?
Sorry, I didn't quite get your question.
What fabrication technique for the material yielded the highest critical temperature? And why did that technique work so well with that material?
I see, okay. You see, the thing is, this is a good thing because they form layer material. So we know its structure, we can do it. And I'm only talking about the high temperature superconducting material. I'm not talking about the hydride. Okay, the hydride, it's very difficult to form, in that. But for the cuprate material, in order for them to have that superior superconducting properties, all the atoms have to line up, for miles long. So this is the challenge, for them. So they are using MBE or CBE method to produce them. So that's the cost issue involved. Because right now, many of the, I show you many of the applications examples, but it turns out some people ask, if they are so good, how come we don't see them in the commercial market? The problem is difficult to make, So now one of the things, can we really, from synthesis processing point of view, lower the cost? And then in the same time, we also propose, why don't we operate at slightly lower temperature, but not that low? For example, many people are talking about operating all these things with liquid nitrogen. Liquid nitrogen is fine, but then the performance usually are not so good. So then you have to process it and then get it so that all the atoms line up in two-dimensional perfect form, And then but if you lower the operating temperature, the requirement can be relaxed. And then in that sense, you can also lower the processing cost. So there are lots of possibilities, but one really have to look at the overall pictures and try to make it practical. So there are lots of people working on it at this moment, particularly the group at MIT at this moment looking at that. Mm-hmm.
Dr. Chu, thank you so much for a really fascinating talk. My question is two parts. First, how do you come up with the compound that you're going to try? I'm sure you're not just randomly trying out different combinations, but what's the process? And how many different materials do you try before you have a success? What's your success rate? And second part, sorry. A gigapascal is a really high pressure. is it even commercially feasible to try and do something that can achieve that kind of pressure? Thank
That's
you.
right. Yeah, usually people, scientists, only tell you the good results. And writers also, I believe, some of the famous writers said the most valuable things for them is the wastebasket, So the same thing for experimentalists, you have to do that. And I can tell you, I lost lots of bets with my former students. Every time I said, this is very good, try to excite them, so so they will have interest in to work on it. And so I always say it's going to be a high superconductor. It turns out, I said, if I lost, I'll buy them hamburgers. I spent quite a bit of money on hamburger because I lost most of the time, at the beginning. But anyway, during the study, we not just look at the end results, we also look at the processing during the trying. We say, what are the major factors involved? For example, the layer compound. So then we immediately focus on the layer aspect of the material. And then so that will reduce our scope of effort. The second question is about high pressure. You're quite right. Actually, high pressure plays a very important role for our discovery because because of time, I'll only show you in slides. For example, we saw indication of superconductivity for a long time, So then we said, we look at it, why, But they are not stable. But then in the same time, when we apply pressure, we can see the TC goes up, That means pressure can stabilize the high temperature superconducting phase. So therefore, we look into atomic size, You look at the YBCO, original lanthanum BCO, yttrium is smaller. So we say, can we use the chemical pressure instead of physical pressure? And that's how we stabilize it. And then once we are sure on that, we discover 13 new compounds with that superconductivity. In fact, in a few days, I should mention, actually during the discovery, I was at Harvard giving a talk, and I was, my lab calling me every hour, give me a point. So I have all those points in those days, we had to use transparency. And that's how I did it, So to answer you, yes, okay, about the pressure, so we know that. But then what about application? We also realize, particularly right now, in the predictions, in our observation, even in the Cupric material YBCO, really high temperature was obtained under high pressure, like 31 gigapascal, right? So that's why now we try to develop a technique to remove the pressure and maintain the high pressure induced superconducting phase with high TC. That's what we are working on. And I show you we have preliminary success on that, at this moment. But whether we can get to room temperature superconductivity without pressure, please stay tuned.
Great talk. I'm Jose Pagan at the University of Colorado Boulder. I'm a plasma physicist, so a graduate student, and so correct me if I'm wrong, but I like some of this stuff as a hobby. So there's been a lot of research at Rice trying to expose materials that have these exotic flat bands and are allowing to actually change lattices to different configurations to try to expose some of these exotic materials. Or exotic properties. Is there some form of future that you can see where we can kind of link these two, like maybe quantum computing and all this, to having something at like a room temperature superconductor where we can control these states and control these lattices that transfer between like a Kagome lattice to a Lieb lattice?
Yes. Because for example, right now, we call it pressure quench technique, try to get high TC without pressure. And that effort is supported by a venture capitalist and who happens to be the founder of either Microsoft or, so therefore, and they, together with us, file patent for the potential application of this material, yes, and also technique. I don't know whether I answered your question or not.
No, it's yes, you did. Thank you.
Yeah.
Thanks again for your talk. Thank you for slowing down and explaining the science as well at the beginning. I appreciate that. My question really relates to the quote that you have here and the state of our world and the state of our countries and what the future might hold. I guess I'm here talking with someone who's met presidents. I guess I'm just wondering, how do you see the role of science and scientists in particular in beyond the laboratory or beyond these meetings in terms of shaping what I would call culture and the way that these applications sort of play out and the way that they affect our world and our everyday interactions?
Yeah, I think this is a very interesting question because, really, scientists did not play any role in the old days. It started playing important role in politics after the Second World War because of the atomic bomb. People really believe in that. But have scientists really lived up to that expectation? And many of them do, but not everyone. As I show the data, in one of the persons, claimed he got the room temperature superconductor, and then turns out later on people found it's not there. And these are very bad for us. But the thing is this, I think we have to be patient, we cannot overclaim, and it takes time to do it. But the high temperature superconductivity generates lots of hype, but in a sense, we also, because the hype also damaged the field to a certain extent. At that time, if all you have to do, just say you're working on high temperature superconductivity, money flows, to you. But turns out people also have expectation. They say, where are the products, And the products right now has not appeared yet. I'm talking about commercial product. Niche products are there, But you usually would really like to have commercial products in order to impact the world, So it's not there. But so I really a little bit concerned about some of the fields at this moment, also including bio, overhype, on that. And eventually we have to pay because when people got excited and pay for our work, and they will ask for something in return. But so that part, science integrity, is very important. We have to do it. And we have to let the world know that science itself, science, of course, is neutral. It will do us good, but also do us harm. I remember when high temperature superconductivity just appeared at the time, I already talked to some people, a thinker, they are thinking about what about its destructive power. Indeed, if it really worked out the way we want, it can also destroy lots of things. I don't know whether I answer your question or not, but in general, that's what I think. Yeah. Thank you all for sitting through this.
So I have a hopefully quick question. Can you speculate on the mechanism that allows the superconductors in these hydrides to maintain their superconductivity after you've released the pressure?
Yes. No, I agree to speculate, okay? But doesn't mean I know the answer. Right now, it appears to me, as I mentioned in the beginning, whenever you have electrons formed pairs, and then that's the requirement for superconductivity to occur. And you want that attraction to be strong enough, so therefore the pair can survive high temperature, So that's the whole thing. And even though now many people talk about non-traditional superconductivity, but they are still talking pair, All they say is it's not BCS superconductor, and that's not quite right. BCS theory, basically, although they mention that attraction is due to electron-phonon interaction, but it can be any other things, like a magnetic fluctuation and all those things can happen, So therefore, at this moment, that remains to be an open question. No one knows what specific interaction between them. Let me tell you, original people said, phonon, that's a lattice polarization. Magnons, the magnetic fluctuation, and then even finally getting to anion, and then later on even getting of demons, okay? Anything at an ON at the end will work as an excitation, provides attraction. So, but nothing really definitive at this moment. All you have to do is get an attraction between electrons. If you can generate it, then it will get superconductivity. If the interaction is strong enough, they will get a high TC. Yeah.
Thank you for your talk. I have a question. Why does high temperature superconductivity need high pressure? Usually pressure higher, temperature higher, super electron is supposed to transport harder. What the reason for that?
I see. You ask why we need high temperature, high pressure to get high TC, right? That's your question, am I correct? Right. You said why high pressure is important. I should mention, not all superconductors under high pressure will get TC higher. Some of them even disappear, okay? In some of the material, if the material is right, band structure is right, then you can get it to high TC. It happens in the hydride material. Hydrogen, the energy spectrum, under high pressure, it can get some modes, lower its temperature, lower its energy, and therefore get into the Fermi level, and therefore it gets a high TC, but it's not definitive. It can be either way. But in order to get that state, turns out at this moment, pressure is the best way to get that crystal structure, and then get to the high TC.
Thank you.
One more.
Okay. Sorry. I know about 30 years ago, somebody did experiment about using the superconductor to shield the gravity. Are there any recent experiments about that?
No, I don't quite understand the question.
Okay, I can say again. About 30 years ago, I saw some paper about the experiment using the superconductor, like a superconductor disk. They measure the gravity about the superconductor, like a sample, the weight loose. That's they declare about the gravitational shielding.
Oh.
And do we have some lab still working on that to try to do such kind of experiments further?
I didn't quite understand the question. Did you say looking at gravitation using superconducting method?
Using superconductor to shield the gravity. Oh,
there are lots of not a lot, quite a few experiments. They're using that method. Turns out it was not decisive. It was not decisive at the time. I think in terms of gravitation, I think we have an expert, two of them sitting there from U of H. I think Renee, and they know better on that, gravitation. But sorry, that's not my field. But I did read some of the report. They tried to do it. For example, some of people even said once superconducting, and the mass will be reduced,
Right.
But later on, it was not reproduced,
Yeah, somebody say like a superconductor generate like a scalar field. They can reduce the gravitational constant around,
Right.
and then the lost gravity also. So if that happened, the space transport, space flight, that's a real revolution maybe.
Yeah, in fact, there was a report. In fact, the paper was published in PRL, Physical Review Letters, on that, That means once you get two superconductors and put more, finally, gravitation disappears, I remember that, and they had a nice scheme to describe that, but turns out it was not reproduced.
Okay, thank you.
Yeah. Okay, thank you.
Let's thank our speaker again.
Thank you all.
Just a few remarks before I close the session. We're getting close to the end of the conference, so it's very important for us to hear back from you, your feedback, so we can improve and have a better conference next time. So what's going to happen through the day is that there's going to be QR codes that you can use, and then we really, really appreciate your feedback, to make things better. Positive, negative comments are really welcome. And with that, I close the session. Thank you very much.